say something about the exercise class for first day. So before starting, with the theory, let me say that on Thursday we will start the first lecture about exercises. And ciao Jimmy. So if I think that in the email that you received there should be a PDF file with a list of the exercises, and so if you want to solve them quite with every detail, you need a lot of time, because they are quite specific. In particular, I think exercise 3, and it's quite technical, and you need to be quite smart to solve it. And so the theme about the exercise class will be topological group. So in particular, I think that the first one is to prove that OPQ is not compact if P or Q are both greater or equal than 1, and then you have some property about suitable neighborhood of the identity, and then what? And then the modular function, because today we are going to talk about R measure. So far we describe a little bit topological groups and how essentially topology and algebraic property try to talk each other. And today we are going to introduce a new character in the play, that is measure theory, which is quite amazing for doing that stuff, because with measure theory you can do a lot of stuff, like, let's say, functional analysis, ergodic theory, and everything. It's quite cool, and it's quite cool. And then, so exercise 3 and exercise 4 are about R measure and properties, or the so-called modular function that we are going to discuss today. But for the room, I think that Thursday we are going to be not here, but in Georgia. Dove sei, Filo? Dov'è Pippo? Qua, là. Di là, vero? Geology G3. So, shit happens. And so first, for Thursday, the room is G3. Georgia. And let me recall you that next week the theory won't be on Tuesday but on Thursday, because there are 2 seminars of the geometry group, so we needed to shift and to move the lecture on Thursday. And so for the exercises, those that are PhD students, so I won't solve in the lecture every exercise. So I will cover some part of the exercise sheet, and the rest you have to do by homework for the exam, let's say. And okay, and guess what? Maybe we can start. Question about the exercises? Not. Questo è Davide? No, è lì Davide. And so that's it. So that's for the exercises part. But also, hopefully we will try to to stabilize for the room. So we will see. So for today, let's go back to the end of the previous lecture. We were speaking about some strange property about topological group, and was proposition, I don't remember the number, proposition 8, 7, whatever. 7. So proposition 7, what you have is that essentially is telling you that you can focus your attention on closed subgroups of topological groups, because if you have open ones, they are immediately closed, and if you have a group, you can close it and it is still a topological subgroup of your group. And then there is some strange property regarding the connected component of the identity, which is surprisingly a subgroup which is normal with respect to the ambient group, and you have also that if the group is connected, then you can essentially generate it using any neighborhood, any symmetric neighborhood of the identity. And the last part was about discrete normal subgroup, and if you have a normal discrete subgroup of your group G, then what you have is that immediately it has to lie in the center of the group. And the center is who is the center? Let me recall that the center are the element X in G, such that X and G are equal to Gx for every G in G. Okay? So we needed to show this last statement, and here. So now there is the trick. So proof. So what's the trick? Take for any n in n, we can define the following map. Phi n from G to G, phi n of G, G n G minus 1. But now, since n is normal, what you have is that the image of phi n must lie inside n, because n is normal. Right? So somehow, what can we do is we can substitute G by n. Okay? But now n is discrete and G is connected. So, scrivo di qua. So now, no, voglio scrivere anche lì. So now if we take f minus f phi n of n, what we have is the following. So what is this stuff? Are the element in G such that phi n of n is, or phi n of G is equal to n, and we can write it G n G minus 1. So since G is connected, so n is discrete, so in particular little n is open in n, in big N. Since n is discrete, is open, and you can, and in particular this means that phi n minus 1 of the n is open, because clearly this is a continuous map, because we have that G is a topological group, because so phi n is continuous since G is a topological group. But now you can check by yourself that the preimage of this point is a subgroup of G, and hence, so by point I don't remember, I think 2 or whatever, what we have is that phi n, because G is connected, because it's both open and closed, and so it must be G. Okay? And since it, I mean, we pick any element of n, what we have is that n lies in the center. Done. So discrete subgroup of topological groups, in particular discrete group of Lie groups, we will see, maybe, I don't know, maybe we will see that they are quite important. In particular, if they admit also an invariant measure, they are called lattices, and lattices are amazing, really amazing. So today we are going to talk about the next chapter that we introduced last time, which is about R measure for locally compact group. So why R measure? Because I mean, if you put yourself, you are adding a new ingredient in your theory, that which is measure theory, in order to see what happens if you want to relate measure theory and the algebraic and the topological property of the group that you have. But first, let me change side of the paper. So let me record the following. So for me, notation, let's say. Notation. First, so let G be a locally compact Hausdorff group, and let's say that X is a locally compact Hausdorff topological space. So for me, I mean, we are going to see what happens if G, since I will need this notion also in the following lectures, I will write that G acts on X if there is a homomorphism, if there is a homomorphism, let's say tau from G to the homeomorphism of X. So in this case, we are saying that G acts by homeomorphism. By homeomorphism, if there is a, I will call also a representation, let's say, of G inside the group of homeomorphism of X, and instead of writing tau g of x, where g is in g and little x is in x, we are going to write what? G dot x or gx without anything. I mean, I know that it's quite boring, but we need to fix the notation once and no. So another thing that I'm going to use is the following notation, is C00x. So this is what? The function from x, dove voglio? Let's say to C è uguale. Vabbè, ci va bene. F continuous and with compact support. So maybe in the course that you had, you saw CCX instead of C00, but I don't like it, so I won't write CCX. And why we need C00? Because somehow we need to realize some suitable functional on this space, linear functional. So in particular, let me say the following. Come l'ho scritto? Remark? Come l'ho scritto? No. So assume to have an action of G on X. That means a representation by homomorphism, whatever. Now, so in particular, what you have is that you can use the action of G on X to define action. Cosa sto scrivendo? An action on C00x in the following way. So we define a representation lambda from G to what? We need to define some invertible linear homomorphism of C00 in the following way. So here you have an element G. Where does it go? So you need to act on functions. So lambda G applied to F, and then you need to evaluate on X. By definition, we say that this is F G minus X. Okay? So somehow the action of G on X allows you to induce an action on the space of linear invertible application of C0 in the following way. I mean, you apply, you need to know what is the action of G on the function, and you need to evaluate it on a point, and what you do is to you use the action by G on the point for the function f. So we say that non mi ricordo il numero, 8 forse. So the representation lambda is called regular representation of G for or into, let's say into GL. So I'm not doing here any distinction between left and right action so far, but we will see, since we will use the particular case when X is a group, then we'll have two different actions on G, left translation and right translation. So we will see how these both the action, let's say, are important for us. So what? Who cares about this stuff? So we can define also, so sorry for the list of definition, but we need it. So we need also C00X dual. So for me, what is the following stuff by definition is the set of lambda from C00X into C linear functional. So for me, this C00X star is the dual space. And now let me recall. So let me recall what does it mean for a linear functional to be positive, and then we are going to remember a quite important result in functional analysis, which is Riesz representation theorem. So a functional lambda from C00S to C is positive if so what is lambda? So the argument of lambda are continuous function on X with compact support, and we are requiring that this is a positive real number whenever f is a positive real function. So if you are afraid by C, then you can put yourself into R and reason on real function, and that's fine. So why positive, linear, whatever, blah blah blah. So take the integral. Take an integral of a positive function with compact support. What you get is a positive real number. So somehow integrals are like the main example of this object. Indeed, Riesz representation theorem tells you that any such functional can be realized suitably as an integral with respect to some suitable measure. That's the main idea of risk representation theorem. And let me recall you, so theorem risk, lo voglio scrivere decentemente, quindi non mi serve più. So let take any element in here. So what you have is that lambda is a linear functional, and let me positive linear functional. Then what you can say is that there exists a regular, let's say a Borel measure on X, Borel measure mu, such that what? Such that lambda f can be written as the integral over X. No, in this way, as an integral. That means that lambda can be realized as a suitable integral with respect to a Borel measure, and Borel measure are somehow measure which behaves well with respect to the topology of your space. Because remember that when you have a Borel space coming from a topology, what you have is there are F sigma and G delta sets. That means sets that you can approximate using open and closed sets, and you hope that your measure somehow behaves well under this kind of approximation. So someone can ask me, so what? So where is the group? Why we care about this stuff for groups, and who cares? A lot of people. So far we supposed to have any topological space X which is local. A key point in here. Key point. In order to apply in a suitable way risk theorem, one of the hypotheses that you required for X is local compactness. So local compactness is crucial. And that's why we are going to take locally compact groups from now on. Actually, Lie groups are even more nice, but we can think about locally compact groups. So far we ask for we have taken any locally compact topological space X, and we are saying, well, if I have an action, I can say something, but somehow all this stuff, in particular this object here, this statement here, does not talk with the G action that you have. I mean, they are quite independent. So now the idea is to ask the following. Take X equal G. And now we want to somehow understand what happens in the case that when X equals G. So if X equals G, then if taken. We have two different representation of G inside its homeomorphism, at least two, which are quite standard. So I'm going to call the first lambda, no, maybe no, maybe not so smart, L from G to homeo G. So L G is equal to our friends LG, left translation. What does it mean? Let me recall you. Left translation of an element X is Gx. In the same way, we are going to define R G of G inside homeo G. Rg is by definition Rg, that means right translation. Okay? So now we can ask something. We can ask what happens if so in particular what we have in particular, this implies that we have two different actions of G on first, let me say, see the space of continuous function with compact support on G. And in the same way, and also on the dual space. So on here, and also on the dual space. Because you can use both left action and right action in order to see what happens to continuous function first and then to linear functional. And that's what. So maybe it's an exercise. I will give you as an exercise. Let's see. Sure, why not? Exercise. So please check by yourself. So exercise.
The right action doesn't change the order of composition.
Sure, I mean it's the typical thing that when you have a right action, you can obtain a left action by using the inverse, and this fact that you have, it depends on how you write it. Clearly, if you have right action, you need to use G1, G2. It's quite relating on notation on how you write it. But if you write it like, let's see. So maybe you can use -1. -1. Thank you. Every time that I have right and left action, I can get pretty confused. So this is Rg -1. Thank you. So what we want is to study linear functional that are somehow invariant under the action of G. That means that, so first the exercise and then I will do some comments. So the exercise is the following. So take lambda, dove lo facciamo? So now I will give you an exercise relating on the more general setting that you can put x in here instead of g, but it's not important. So suppose to have a positive linear function, take a positive linear function. So check that if you have, I didn't define it, I think. Maybe no. No. So I need first to define the action. So again, when you have G acting on X and you have G acting on C00X, you can define another representation, which is lambda star from G to what? G as C00 X dual, defined in the usual way, applied to lambda, applied to F, if lambda minus 1 of F. So every time you play with inverses in order to put you inside the linear functional. So this is another action of G induced on linear functionals on C00. And what I would like to check is the following, that check that lambda star G lambda correspond to G down star mu, where mu is dai cancellino qua, where mu is the measure, is the Borel measure representing lambda according by Riesz theorem, and the following notation is the push for measure. So first let me ask you, do you know, everybody know the notion of push forward with respect to a measurable function, or no? And so let me recall, let's say, definition. Let's say in this case, in this particular case, what we have X mu measure space. And supposed to have a function from X to Y which is measurable. Then you can define f push forward of mu of a set in here, let's say B using the following way: mu of what? F minus 1 of B, where B inside Y is measurable. Why does it work? Because you take a measurable set, the function is measurable, you go back in X, you get a measurable set, and you can take the measure. So that's the meaning of push-forward measure. In particular, what I'm trying to say is that if you apply an element G on a linear functional, then what you are doing is to considering the push-forward measure with respect to the measure that represents your linear functional. It's a computation that you can do by yourself. So in particular, what I want to state now, and then maybe, so in particular, we have an action on linear functional, and for me, I can define, so what? Definition, finally, so definition what? 10? 10? 10, 9, quanto stavano? Non chi se ne frega. 10 facciamo? Definition 10, so left are measured on a locally compact Hausdorff group G is a positive linear functional M from C00 X to C, maybe to R, okay, chi se ne frega? No, such that, which is, let's say, is G invariant with respect to the representation L star, that means the representation induced on this time, this guy here. GL, where L is exactly the left representation induced by left translation. What does it mean more explicitly? Qua. So more explicitly, what we are asking that means what we want. We want that L star G of our linear functional M is equal to M for every G in G. Or equivalently, M of what? Is not, non ve lo scrivo dopo. Okay? So in particular, so remark, direi 11. Since G is locally compact, what we can do, we can represent M as a measure. So we can use this theorem to get a measure, come la chiamiamo? Mu G, facciamo questo vezzo mu G. And what's the property of mu G? If you do the exercise, what you have is that the push forward of mu G is equal to mu G for every G in G. And additionally, and clearly, mu G is such that M of F is equal to the integral of Fg lemma G. So this is by G invariance, and this is by the fact that you are representing your linear functional M using using what? Using Riesz theorem. So what you are saying in the end is the following. Maybe I want to write X. Let me say X. So what does it mean to be G invariant in this case? If we write down, is that coincide with what? Ciao. With the following. For every G in G. So why this formula? Direct measure theorem, do you know how to write it down? So what? Troppe cose di allora. Comunque, theorem push. So this is an exercise for those who are. Cioè la R, forward o forward? Forward. Grazie. Push forward. What does it mean? If you have from X to Y, and you have what? Let's see. Non ricordo neanche l'ipotesi, quindi ci mettiamo il comma. Qualcuno magari che sa l'ipotesi meglio di me le dice. So take f from X to Y be a measurable function and supposed to have a measure on X, and consider a push-forward measure on Y. So what I would like to say is that integrable function on Y can be written in terms of composition of f in some sense. That means that if you can write down, so I'm not writing the exact statement because I should remember the hypothesis precisely, like integrability, something like that, but let's say you can write down, let's say that you have H from Y to R, which is integrable with respect to F star mu, then what does it mean? You can write it as hy df star mu y, and the fact that you can use this composition formula to realize it under suitable hypotheses that I don't remember precisely. So there, if you apply this realization theorem, what you have is that this is the integral of g of fx d what? G down star mu g of x. Okay? And so, I mean, G invariance boils down to this condition here. So now let's have a break, and then we are going to talk about modular function.